Hello, everyone. I'm going to solve the problem that I gave you in class to work in groups. Um, I'm not going to go into the details of the calculations, but um, I will leave that up to you. We're going to go do the procedure for solving this problem. So let's read the question first. John is driving a van on a single lane section of the Sea to Sky Highway. In order to pass a bus, he crosses the yellow line and passes and speeds up to 126 kilometers per hour. At the same time, a truck is coming in the opposite direction with a speed of 90.0 kilometers per hour. When the two vehicles are 144 meters apart, both drivers hit the brakes, which results in a constant deceleration of 6.00 meters per second squared for both vehicles. Draw the VT and XT graphs to determine whether or not the two vehicles will collide. Okay, so the first thing that I ask you every time to do it is to draw a sketch. Draw a simple sketch of the situation. So let's say we are looking at the scene from the top. From the top, we are, for example, on a helicopter, on a plane, and we're looking down the highway, and we're seeing the two vehicles um, approaching each other. So one vehicle is here. One vehicle is here. You can draw the other vehicle here. It's up to you. I prefer to do it this way, and there is no reason for it. It's just I do it this way. It's as I said, it doesn't matter. So one vehicle is has the initial velocity of 126 kilometers per hour. So initial velocity for vehicle 1, V01. Let's call this vehicle 1 and this vehicle 2. V01 is going to be equal to, sorry, just a second. Yeah, for a moment, my computer, the software froze. So here, V01, it's going to be equal to 126 kilometers per hour. And there is the second vehicle, V02, with the initial velocity of 90.0 kilometers per hour. Okay, so I'm going to write down the known and unknowns parameter here. So here I will write down the parameters, V01, V01, and V02. Okay. Now, I need to, these are basically the speeds of the two vehicles. I need to give them the direction. So they're moving in the opposite direction. I cannot lead them with the same sign. If both of them have basically positive velocity, that means both of them, they move in the same direction. So here comes, we need to draw the coordinate system that we choose. So for example, I decide that my coordinate would be y-axis, and it's going to be in this direction. Positive axis is going to be in this direction. Then V01 becomes positive or negative. V01 is going to be positive. So positive 126 kilometers per hour. V02 is going to in the opposite direction of positive y. It's going to be negative 90.0 kilometers per hour. Okay, now I'm going to erase the numbers to make my picture less busy. Okay, and in the picture, all I need to know is that, okay, this is going to be my V01, and this is going to be my V02. I'm drawing an arrow on top of B01 and B02 to remind myself they are vectors. We're gonna do vectors next week, and these things become more apparent for you. Anyways, okay. Now there are other noun parameters. Um, let's say thinking about their position. If I want to know their position, I need to set up 0 on my y-axis, where I consider to be my y-axis, the 0 on the y-axis. I prefer to be the 0 to be here, but you can have the 0 anywhere on the y-axis. And as we practiced before on the um, example of throwing a ball at the edge of the cliff and the ball hits the ground, it doesn't matter where you set your 0 on the y-axis or any of axes for that matter. Um, so that's going to be the 0 on the y-axis. Okay, no, I can know what would be the initial position of each vehicles. Let me write down all the information related to the second vehicle in another column. Okay, this is going to be V01. Okay, and X01, you can call them vehicle A and B. It's your preference. X01, it's going to be equal to, or sorry, Y01, I'm dealing with Y-axis, Y01 is going to be equal to 0. It is on 0, right? It is on 0. And let's say for the V02, we know that V02 is going to be in the opposite direction. We said, okay, it's going to be 90.0 kilometers per hour. Okay, and Y02, the initial position of the second vehicle is going to be, what does the question say? The question say that they are 144 meters apart when they see each other, when they first see each other. So this distance is going to be 144 meters, right? So, and this is because I set my positive y-axis upward. This is going to be 1, 2, 3, and so on and so forth up to 144. Okay, so I'm going to have this at 144 meters. And let me erase this again to have the picture less busy. Okay, what else do we know? What else do we know? We know that once they see each other, they're going to put their foot on the brake and they're going to decelerate. They are going to decelerate with the same deceleration, 6.00 meters per second squared. Now I know A1 is going to be 6.00 meters per second squared, and A2 is going to be 6.00 meters per second squared. Do I need to give them a sign, positive or negative? Yes, of course I do. So if the vehicle 1 decelerates, we said any time velocity and acceleration have the opposite direction, the object decelerates, right? So the acceleration is going to be in this direction, A1. That A1, this vector A1 is going to be in the opposite direction of B01. Is it in the negative direction of Y or in the positive direction of Y? Having the positive direction of Y to be upward. It is in the negative direction of Y. So this is going to be negative 6.00 meters per second squared. And A2, B02 is going in this direction. So that's the initial velocity. Okay, and the driver puts their foot on the brake, and that results in deceleration. Deceleration happens when velocity and acceleration have opposite direction. So you expect the acceleration for the second vehicle to be in the opposite direction of V02. And this vector, is it in the positive direction of y or negative direction of y? It's in exactly the same direction of y. So I will give this positive. Okay. So these are basically my noun parameters. Now, what are the unknown parameters? The question is basically asking us to draw in in words. The question gave us the situation, this explain the situation that you're dealing with, and now it expects us to draw position time and velocity time graph and determine whether or not the two vehicles collide. So one strategy that we talked about in class when I moved around in class and looked at each group solution, um, was that even if you want to know whether they collide or not, um, you don't need to necessarily draw the position time graph and velocity time graph. What you can do is figure out the stopping distance for both of the vehicles based on this initial condition that they have. So uh, let's say in the we know that the distance between the two vehicles, this distance I'm drawing in green is 144 meters, right? If vehicle 2 moves a distance of, let's say, 30 meters and it stops, and vehicle 1 moves a distance of, um, let's say, 40 meters and it stops. So the stopping distance for vehicle 1 is going to be 40 meters. The stopping distance for vehicle 2 is going to be 30 meters. Would they collide? No, they won't collide. So what you determine is that the total distance that they travel, 30 in this case, plus 40 meters, which will give you 70 meters, is less than 144 meters. Is less than the distance that basically the both vehicles that they see in front of each other. So this will tell you that they will not collide. But um, if the stopping distance for the vehicle 2 is, let's say, 100 meters, and the stopping distance for vehicle 1 is, let's say, 60 meters, would they collide? Yes, they would collide. They would collide. Um, 60 meters is the distance that vehicle 1 needs to come to a full stop. 100 meters is the distance that vehicle 2 needs to come to a full stop. Okay? If you add them up together, 100 plus 60, that will give you 160 meters. Is that enough for no collision? No, no, it's not enough, unfortunately, and they will collide. They will collide even before they come to a full stop. They will collide uh, at this point or any point, yeah, at this point or any point depending on their stopping distance that they need. In this example, at this point that I drew. Okay. So what you can find out is the stopping distance for both vehicles, and then determine whether that stopping distance would be enough for the vehicles to come to a full stop. So how do you find that? If they stop, so our strategy is to we're gonna, for a moment, we're gonna forget about position time and velocity time graph, and we're gonna think about whether they collide or not. Okay. Of course, you can first focus on drawing position time and velocity time graph. But since this strategy came up in class, I'm gonna explain it. Uh, if they stop, final velocity of 1 is going to be 0, and final velocity of 2 is going to be 0, right? And um, we want to know we want to know what would be x1 final and what would be x2 final. Where are those distances? So let's continue. I don't know this. Let me go back to this color. I don't know this, and I don't know this. Okay. Uh, how can I find that? So remember, we have three equations that we can always consult with. V is going to be equal to, I'm going to write them down. V0 plus AT, sorry. V is going to be equal to V0 plus AT. X is going to be equal to X0 plus V0T. Plus half AT squared. V squared is going to be equal to V0 squared plus 2A times X minus X0. Sorry for my writing. It's my surface is at a position where I don't have very good control on the screen. So very good control when I write on the screen. Okay, so we had this three equations for one-dimensional motion that we talked about, and this is for the x-axis, but we can write it down for the y-axis as well. Okay, and here I need to make this remind myself I am on the y-axis, y1f and y2f. Okay, now let's find the stopping distance for vehicle 1. V squared is going to be equal to V0 squared plus 2A times y minus y0. Okay, so if I write it down for the first vehicle, I'm going to label this V1F, V10, A1, and Y1F, and Y01. And if I write this down for the second vehicle, V2F is going to be equal to V20 or V02, doesn't matter. V20. So remember here, I wrote V02, V20 and V02. You can exchange the indexes here. V20 plus squared plus 2A2 Y2F minus Y2 Y02. Let's have this Y20 and this have Y10 to be consistent here. And I'm going to make this V10, make this V20, make this Y10, oops, Y10, and here Y20. Okay. V1F, V2F. But as I said, you can interchange the indices. It's not going to be a big deal, and they basically mean the same thing. Okay, now the only thing that I need to do is to plug in the numbers. So for example, for the first equation here, V1F, I know it, and it's going to be equal to 0. V10 is going to be 126 kilometers per hour. And it would be a good idea to convert that kilometers per hour to meters per second. Plus 2a1 is negative 6.00 meters per second squared times y1f, which I don't know it, y1f minus y10, which is equal to 0. Okay, and you're going to do basically the same thing um, for the second vehicle. Remember, guys, here I put down the units in my equations. I didn't do for most examples that we solved in class. I didn't put them into the equation because I made sure before plugging in the variables that everything was in SI units. By here, they are not in SI units. But if you made sure that you converted 126 kilometers per hour to meters per second, then you can plug in that numbers in meters per second and don't worry about writing down the units. So here, after solving this equation, you will find out y1f, and you will find y2f. Okay, so where are they in this diagram? Y1f and Y2f. So Y1f would be the distance, the stopping distance, F for the stopping position for the first vehicle, and Y2f is going to be the stopping position for the second vehicle. Okay, how do you know whether they collide or not? You need to find basically the displacements for both of them. The displacement delta y for vehicle 1 is going to be equal to y1f minus y10, and the displacement for the second vehicle delta y2 is going to be equal to y2f minus y20. Okay, and this is not going to be this is very important, especially when you do this, because y10 here is going to be equal to 0, right? For the first vehicle, it's at 0, but y20 is not equal to 0. So don't stop calculating when you get y1f and y2f and add those numbers up to see if they collide or not. You need to find the displacement. So you will find out delta y1 and delta y2 and then add them up, plus delta y2, and then add them up, and you will get a number. You will compare that number. You can call it delta y or whatever you want. Compare that number. Let's call it delta y, or let's call it delta y total. Makes much more sense. And compare to 144 meters. And remember, you want this to be in meters. And the only thing that you need to do is convert those 126 kilometers per hour and 90 kilometers per hour to meters per second. Compare that to then compare delta y total to 144 meters. If delta y total is going to be smaller than 144 meters, then there is no collision. So if delta y total is less than 144 meters, then there is no collision. If delta y total is going to be greater or smaller than 144 meters, then there is collision. I think from the calculations that some of the groups did in class, they found that delta y total is going to be greater than 144 meters, and they found that there is a collision. So this is basically the approach that you want to do, that you want to take to see if they collide or not. Now, let's take a look at the position time and velocity time graphs. Okay, let's start from the, let me change my color. Let's pick blue. Um, let's see if we can first come up with an idea to draw the velocity time graph. Okay, um, let me extend the velocity time graph to the negative parts for negative velocities. For car one starts with a velocity of, this is car one. It has a positive velocity, and its initial velocity is positive 126 kilometers per hour. So of course you need to convert this to meters per second. Um, so it would be meters per second, and t is going to be in seconds. Always label your graphs with the right label and then in brackets the units. Um, so this is going to be whatever number that you can that you convert v01 to. I'm gonna I'm gonna write down just v01, 01, whatever number that it is after you convert it to meters per second. Um, the um, the the car one is going to slow down, right? It's going to decelerate. So, and its acceleration is constant. So, if acceleration is constant, so if I draw the acceleration time graph, let me draw the acceleration time graph here. The question didn't ask for acceleration time graph, but let's draw it. Acceleration, meters per second squared, and time per second. Acceleration of car one is going to be equal to what number? It's it's always constant, and it is negative 6 meters per second squared. So this is car one. I'm going to label it. This is car one, and this is negative 6.00 meters per second squared. I don't need to write down the unit because the unit is given in the bracket. And car two accelerates with positive 6 meters per second squared. So this is approximately the same. Okay, I'm gonna label this car two, and it's, let's even change the color. Let's use another color. Let's pick, I don't know, purple for car two, and this is going to be 6.00 meters per second squared. So we want to draw the velocity time graph for car one. The velocity time graph that results in a horizontal acceleration time graph would be a linear line, right? A linear diagonal line with constant slope of negative 6.00 meters per second. So it's going to be, let me pick blue. We use blue for car one. Okay, this is going to be car one, and its velocity is gonna be a diagonal line with a slope equals to negative 6.00 meters per second squared. And this is car one. What's going on for car two? Let's pick purple. Um, it starts with the velocity of negative 90 kilometers per hour. You will convert that to meters per second. So I'm gonna draw it around here. This is gonna be V02. And of course you will plug in the number that you found. And uh, this is the velocity time graph for car two should give you a horizontal positive acceleration time graph. And that would be a diagonal line with positive slope. So this slope is going to be equal to positive 6 0.00 meters per second squared. Okay, and this is car 2. No, no, let's take a look at position time graph. What type of graph? What type of graph gives you? If you take its a slope, will give you a linear line graph. So remember, remember what we did? We took a slope. So for example, we said if we have a curved line, curved line, a curved line like this, or a curved line like this, uh, they will give you, if you take the slope, they will give you a diagonal line like this, um, or this, sorry, diagonal line. Yeah, either with positive slope or negative slope. Yeah, positive slope or negative slope. And that if you take the slope of a diagonal line, it will give you a horizontal line, right? So in here you have a position, a velocity time graph that is diagonal, right? It is diagonal. So these diagonal line, they come from a position time graph that is curved. That is curved. Now let's draw the position time graphs. Let me erase this. Let me pick another color. Let's pick, yeah, this type of red. So dark red almost. Position time, x, versus time in second and in meters. Okay, I know that the initial position of car 1 is going to be 0. So I decided, sorry, let's make this y. Why it's not writing? Um, the software is frozen again. Oh, it's working now. Y in meters. Okay, because I set up my axis as y-axis. You can have it as x-axis. It's up to you. Okay, I know the initial position of the vehicle 1 here. I decided that y01 is going to be equal to 0. So that's the initial position of car 1. Let me pick blue here, and the third one would be purple. Let me pick no blue. The position of the first car is going to be, the initial position is going to be 0. And it should give me, I should draw a curved line. I should draw a curved line um, that basically result, if I take the slope, it's going to result in V01. So I have a linear diagonal line. It's going to give me a curve. Should I draw this curve or this curve? And remember, all of these curves are part of a parabola. Um, and the reason is, if you write down y as a function of time, y is going to be equal to y0 plus v0t plus half at squared. Remember, this is the second equation. The second equation. For any position time, velocity time graph, that basically there is acceleration, and acceleration is constant, they will give you a parabola. The quadratic equation will give you a parabola on the xy axis. Okay, but are we dealing with the whole part with the whole parabola? But no, we're only interested in the part that basically gives us the position time and velocity time graphs. And here, basically here, the position time graph. So I want to choose between these two curves. Which one do I choose? I'm going to take a look at the velocity time graph. It starts from a positive number, and it's going to approach 0. So when I take a look at the slope of this, the slope of, let's see, yeah, it doesn't give me the ruler. The slope should approach to zero as time progresses. So I'm going to take a look at the slope here. This is the slope. It is zero. The slope increases. Is that so? This is the slope here, and the slope increases, right, as time progresses. Is that um, in agreement with what is happening with car one? No, car one decelerates and finally comes to a stop, hopefully, if there is no crash. But what we know about it is gonna start from a velocity, a positive velocity, and it's gonna approach zero as the time progresses. So this is not gonna work, and uh, you need to draw a graph like this for car one. This is car one. Okay. Here, uh, at time equals to zero, the slope is basically the slope of this line. As the time progresses, the slope of the tangent line is approaching zero. Let's see if I can erase this line without erasing the whole graph. Yes. Oh no. What about this line? Zoom in. Yeah. There we go. This is the position time graph for car one. And now let's draw the position time graph for car two. I know, let's move to, let's use purple. I know that the initial position of car two is at 144 meters. 144 meters. This is 144 meters. Okay, and I know that I should draw a curve that when I look at the slope of the graph should give me this line with a with a positive slope. Okay, so I had to so here the vector that we sorry here the graph that we drew for position for car one. And remember, the slope is positive at any given point. The slope is positive. The velocity is the don't confuse that with the negative slope of velocity time graph. Negative slope of velocity time graph represent the acceleration, and it is here. Acceleration is negative, right? But the value of velocity at any given time is always you're looking at this. Okay, now let's take a look at the, let's change the color to purple, and let's take a look at car two. Um, as the velocity is negative. Okay, that means we're gonna draw a curve that is that the tangent point at any given point should be negative. Okay, and based on that, if you not graph, if you not graph, is that what you see? So here it's almost at the slope, basically is that in agreement with what you see for velocity time for car two? Does the velocity of car two start from zero So this graph is going to be this graph, which basically so start from exactly at 144 and so it should be on the negative side of the anyways. Um, so you will deal with this and slope is basically at negative point, slope and zero. Now you have these two graphs, and let's say the two cars collide, as some of you have the class. If the two cars collide, then at this point, the two graphs intersects, at and that means at a specific time, this t of I'm gonna call it tc, c the software after they upgraded this point to some point for so it seems like that it's working now. So if let's say the two vehicle make a collision, and let's make this TC, time for collision, then basically the rest of at the rest of the curves, they don't matter because these are not going to happen in reality. If the two cars collide, then they're going to be uh, at the same position, at the exactly same position. I'm going to call it XC position, or YC, sorry, YC position of collision at at an instant of time. We call it TC. So if the two vehicle collide, then you will kind of this is going to be in seconds, this is going to be in meters, this is going to be 144 meters. For car 2, you will have and this is going to be TC, and this is going to be car 2 was purple, sorry. Car 2, we used purple, and for car 1, we used blue, and they're going to collide like this. So, and this is going to be their position time graph. This is going to be YC. How and if you remember in class, I asked you to find out TC at least. You can find out TC or YC easily. The only thing that you need to do to find TC is to use this second equation. The second equation. So let's write it down for each of them. Y is going to be equal to y0 plus b0t plus half at squared. And for the other car, y is going to be equal to y0 plus b0t plus half at squared. If I write this down for the first car, car 1 or vehicle 1, this is going to be y1 c, okay, v0 1 or y10 v10 times t plus half a1t squared, and this is going to be y 2c, y20, y v20, and a2. Okay, this is going to be the two equation for both of them. And if there is collision, y1c and y2c are going to be exactly the same, y2c, and this is going to be equal to y1c. They're going to be exactly the same. They're going to be exactly and at one position at time tc. And I'm going to call this, sorry, you can call this tc, but I'm going to leave it as t. As you know, I'm lazy and I want to write less symbols as possible. I'm going to make this t curved so that you don't confuse it with the positive sign here. Okay, so if you equate these two together, y10 plus b10t plus half a1t squared is going to be equal to y20 plus b20t plus half a2t squared. Then you plug in the numbers. Let's plug in the numbers. y10, if this moves down, I'm going to see my y10. y10 is going to be equal to 0 plus v01. It was 126 kilometers per hour. I'm going to 126 kilometers per hour. You will convert this to meters per second times t plus half. A1 is negative 6 meters per second, negative 6.00 meters per second squared times t squared is going to be equal to y20. I'm going to take a look. Y20 was 144 meters. Remember, I'm writing down the units because I didn't convert the 126 kilometers per hour to meters per second. Plus V20. V20 is negative 90.0 kilometers per hour times t plus half. A2 is going to be 6.00 meters per second squared t squared. So you equate these two equations. And you will have a quadratic equation, and you will solve for t. One thing that I noticed some of you did, you cancel this term with this term. They don't cancel out. They don't cancel out because one of them is positive 6, one of them is negative 6. They're not exactly the same thing. So in fact, and they're going to add up. So a negative 6 divided by 2 will give you negative 3. If I move it over to the right-hand side, if I move over everything to the right-hand side, I will have 144 meters. And here, plus I have negative 90 kilometers per hour times t. And if I move over this 126 kilometers per hour to the other side, I will have negative 90.0 plus 126. Everything is going to be kilometers per hour times t. You will convert this to meters per second. And on one hand side, I have 6 divided by 2, 3 times t squared. And here, negative 3 times t squared. 3 plus 3 is going to give me 6.00 meters per second squared t squared. So, sorry, I meant to write negative 126 kilometers per hour. Okay, so what you end up with is that basically you add up these two numbers. You will have 144 plus whatever this number is, and you convert it to meters per second. This number times t plus 6.00 t squared. If you have everything in SI, and you will solve you will solve this quadratic equation, and you will get the collision time, TC time. After you got the collision time, you can plug that collision time into any of these two equations to find the YC, the collision position. I didn't ask you to find out the collision position because we didn't have enough time, but I expect to see collision time, TC, in your graph. So yeah, basically this was it. I went into the details of the explanation. For example, here I drew the acceleration time. You don't need to draw the acceleration time. And yeah, any extra details that I went through to make the points clear, you don't need to go through those explanations. But this is basically what uh, I expect to see as your solution. And every time, remember, when you uh, um, before before asking yourself what equation I should use, which is it's a good question, but you should ask yourself at the right moment. First, draw the situation. Draw a simple sketch. See, no one is less talented in drawing things than me. You will draw whatever you can think about the situation. I saw some of you draw the situation like this on the x-axis. If two cars on the x-axis, they have a distance of 144 meters, and you name this x-axis. This is fine too. This is fine too. This you only uh, you only change the name of your axis, which is going to be fine. Or some of you consider the vehicle to the position of the vehicle to be equal to 0. That's also fine. Uh, but yeah, you need to draw the situation, and then after you draw the situation, you write down the known and unknown parameters based on the coordinate system that you set up. Then you should ask yourself which equation I should choose. Okay, hopefully this was clear, and yeah, let me know if you have any further question, and see you in class.